Thank you everyone for joining. We will be continuing with the problems that we were looking at yesterday. And there's quite a few that we did yesterday, but I think we're mainly left with the integral problems. So for those who are not there yesterday, we mostly looked at problems on areas between two sections and the volumes of revolution. So that was basically the first part of the worksheet, and then the remaining parts will be mostly looking at integration, which will cover some of the topics that you guys have just beginning covering, like integration by parts, right? So I stopped here yesterday because this particular problem that we had was asking us to find the volume of the area of the volume of the solids that is obtained when the sine function is rotated around the y-axis, and that sine function is defined between 0 and pi, right? So when we set up the volume formula, we end up getting something like this, which is a form that can be solved using integration by parts. Right. So if you guys have remember what you did in your classes on integration by parts, you know that you have to decide which of the two, rather x or sine x, will be your u and your dv, right? So typically what you do in these cases is you try to stay consistent, because in some cases you might have to do integration by parts multiple times, right? And when in those cases, you need to try to stay consistent with your substitution. So if you say, let x be our u, right? And in consequence, our dv is sine x dx, right? So let's assume that you had to repeat the integration by parts once more. You would have to stay consistent, meaning that the dv function would remain remain being the trigonometric function, and the ordinary x function will be the u function, right? So that's an important point that you need to know when you're working with integration by parts. Please mute yourselves so there's no background noise. Right, thank you. So now that you do that, the integration by parts formula tells you that now you have x is equal to u, right? That means that dx is just equal to du. And if dv is equal to sine of x, v is equal to negative cos of x, right? So now that you know that, you can bring it back to the original function. And what that tells you is, the formula tells you this integral is equal to u times v minus the integral of v du, right? Which in our case is just equivalent to u is x, so x multiplied by v, which is negative cos, so negative cos of x. And obviously, there's a 2 pi out here, right? So just keep that in mind. Let me include it there. So there's a 2 pi there. And right, so x multiplied by negative cos of x, right, minus the integral of v times du. So since you see that v is negative cos and you have a negative there, you can just cancel that to be positive, and then we have the integral of cos x du. Oh, sorry, dx dx. Right. So now solving this, what you get is 2 pi multiplied into negative x times cos x plus the integral of cos, which is just sine x. And remember that this is evaluated between 0 and pi, so when you do evaluate it between 0 and pi, you get first pi, negative pi times cos of pi plus sine of pi minus 0, right? Minus 0, so that would be plus 0, minus sine of 0, right? So that's what you would get there. Okay, just double check that substitution there. Right. So now you know that cos of pi is negative 1. So you have negative pi times negative 1, which is pi. And sine of pi is 0. So that's 0. Sine of 0 is 0 as well. So everything else is 0. So now you have 2 pi squared as your final answer. Right. So that should be clear there. Any questions? All right, so there doesn't seem to be any questions, so let's move on to the next problem. Right, so this problem is asking us to evaluate the integral of x squared times ln x between 1 and e, right? So we know that in this case, we'll be using integration by parts, because all the other methods of integration that we know of cannot help us solve this easily, right? So, and remember, in these cases, what you're trying to do is find the easiest way to solve the problem. You don't want to do anything fancy, because when you're in a test setting or anything like that, or exam setting even, you're trying to work with a limited time, right? So you're trying to time yourself, so you don't need to innovate new ways of solving problems. So that can be in your own time, when you're practicing at home, but in a test setting, you're trying to solve the problem as fast as you can. So integration by parts helps us a lot there. So in that case, right, let's use a different way of substituting for the specific integration by parts compared to what we used before. So let's say, for example, in this case, we let our u be now ln x, and our dv be equal to x squared. Well, obviously it's x squared dx, right? So before we move on from here, right, you might ask yourself, well, why not just use, right? Why not just let u be equal to x squared, right? And dv be equal to ln x. So why not the other way around? So you'll notice that if you use this substitution here, the first part of the substitution is quite easy to deal with, but the second part here, you would have to integrate and find the integral of ln of x, right? Which is not an easy integral to find, right? So you know what I mean. So if you're trying to spend so much time trying to solve this integral here, while you haven't even finished the original question that you had, that is going to cost you a lot of time that you don't have, right?
Hello, sorry.
Yeah, go
What do you
ahead.
mean it's not an easy integral to find? Isn't it like a set thing that integral of ln x is 1 over x?
No, the integral of ln x is not 1 over x.
Oh,
No, that's the
okay.
derivative of ln x, remember?
Oh, yeah. Oh,
Right.
God. Okay. Thank you.
So you have dv is equal to ln x dx. So v would be the integral of ln x dx. Remember, we're dealing with integrals. The integral of 1 over x dx is equal to ln x, right? But the integral of ln x is not an easy integral to find. It does exist, but it's just something that's very tricky to find. And in an exam setting, you don't want to bother yourself with all those extra calculations and those headaches. You don't want to lose so much time on such a small question. So it also takes you some time. With practice, obviously, comes easy, but you'll see that some substitution for integration by parts are easier to do than others. So try to use the ones that make your life easy, right? So that's what we're doing here. Because in this case, we only have to deal with finding du, which we know is just the derivative of ln x, which is 1 over x dx, right? And in our case here, we have to find the integral of x squared dx, which is an easy integral to find because it's just x cubed over 3, right? So that's easy, straightforward. Now we can go back to our original integral, and we know that the formula tells us we have to have u times v minus v du, right? So now that we have that, what's our u? Our u is ln x. Our v is x cubed over 3. So x cubed over 3 multiplied by ln of x minus the integral of v, so x cubed over 3 multiplied by du, so 1 over x dx. And that is equal to x cubed over 3. Never mind about the boundaries, we'll just add them later, but now we're just dealing with the integral. So x cubed over 3 times ln x, which is equal minus, sorry, we cancel the x here, so we have x squared over 3 dx, and that's the integral that we need to solve. So solving that is an easy thing to do. X cubed over 3 times ln x minus, you can take out the 1 over 3, it's a constant, and the integral of x squared is just x cubed over 3, so it's 1 over 3 multiplied by x cubed over 3, which is just equal to x cubed over 3 ln x minus 1, minus x cubed over 9. Right, so now that we have that, we have to evaluate this between 1 and e. So evaluating this between 1 and e, we get, substituting e first, we have e cubed over 3 ln of e minus e cubed over 9, right? And then substituting 1, we have minus 1 over 3 times ln of 1, right? Minus minus, so that would be plus now. 1 cubed over 9, right? And that will be equal to, we know that ln of e is just 1, so that will be e cubed over 3 minus e cubed over 9 minus 1 over 3 times ln of 1, which is 0, so that would be 0, minus 0, plus 1 over 9. So let's evaluate that. This should be 2e cubed over 9 yes, 2e cubed over 9 plus 1 over 9. And that should be your final answer for that. Any questions? Any comments? Again, like I've said, yeah, go ahead.
Can you please explain for me from the step you introduced? I think it's G.
G, where is that? Is it?
I'm not sure where it's G or what, but after you integrated your
It's
no, after,
9.
oh, nine. Thank you.
Oh,
Sorry.
where is that? Is it here? Oh, sorry. I think it's my
It's
handwriting. This should be a 9.
thank you.
Yeah, I know some people write 9 like that, but my nines look like G's. So sorry about that. Let me change that so it doesn't confuse you guys.
Jonathan, so
Yeah.
basically your U should be what's easy to derive and DV be what's easy to integrate.
If you want to think about it that way, yes. Yes,
Okay.
that's a very easy thing to. It's a very nice way to put it. Yes,
Thank
because your DV is the function that you're integrating, so you want it to be as easy as you can. But as I mentioned before, the most important thing, and I'm sure you guys will come across this, and for those who have already watched the videos that I did on integration by parts, you'll see that for some of the integration by parts for trigonometric functions especially, you need to do it multiple times, right? So because the functions, as you can see, um, for trigonometric functions, the integrals just keep recurring, right? So you integrate cos, it goes back to sine, you integrate sine, it goes back to minus cos, and then just all round and round we go, right? So usually what you do is you use that. For those who haven't watched the video, please just refer back to it. But there's a trick that you use. And while you're doing these multiple integration by parts, right, it's very important to stay consistent, right? So if you let your u, for example, be your trigonometric function, and your dv be your whatever other function you have in the question, then when you do your integration, your second integration by parts, your u has to be again your trigonometric function, and then your dv whatever is left. So that's the sort of a trick that you need to keep in mind. But also for your own exercise as well and better understanding, you could try the other way around. So you could try using one specific substitution for your first integration by parts, and then you switch it for the second integration by parts and see what it gives you. But if you see that you keep going in circle and circle without getting to a final answer, then you know you need to adjust your substitution. But it's the advice that we are given when we are studying the module. So, and I think if you actually try it on your own, you'll see that it's valuable advice, right? So, any other questions on this? Okay, moving on then. Let's move on to the second. Right, so we have the integral of tan to the 5x times sec to the 4x dx. And for this problem here, we'll have to use a combination of trigonometric identities and integration by parts. Right, so this is my question to you guys. What trigonometric identities do you think we should use here?
Is it the 1 minus 6 squared x or
Well,
the other way?
that's a good one. So that would be sec squared of x is just equal to tan squared, right? Tan squared x plus 1,
Yes.
right? So you could use that one. or you could use, I think that's the one you're trying to give is the sec squared minus 1 is equal to tan squared. So you would try to substitute the tan rather than the sec. So you could try both ways. So in this particular exercise, we'll try to use the first one here. And then if you guys want, at the end, if we have time, we can go back and try to use this one and see if it gives us a solution, right? So yeah, let's try that. So let's use the first one first. Right, so using that substitution there, we have 10 to the 5x multiplied by, right, 10 squared plus squared x plus 1 multiplied by sec squared, right? Because we substituted one of the sec squared by the identity there, dx. And now expanding that, we have in fact, we don't even need to expand it. We can even leave it like that and just do our integration by part at this stage. So let me ask you, what substitution do you think we could use for our integration by parts? What is our u?
Our u could be that 10 stuff.
Right, so you could use 10. Okay. So let's use 10. U is 10, then in our case, our du, oh sorry, not du, but that would be dv. Our dv is sec squared dx, right? Because we know we can easily find the integral of sec squared because we know that's just oh, sorry. We're using u substitution. Sorry, my mistake. I think we oh yeah, my mistake. We're using u substitution here. I don't think we need we need integration by parts, because if you substitute u by tan x, then we have du is equal to what? Is equal to sec squared x dx, right? And then that means that dx is just equal to du over sec squared x, right? So doing that, we can then bring it back to the original expression, and we have now u to the 5, right? You write it nicely. U to the 5 multiplied by u squared plus 1 multiplied by sec squared, right? X dx. Oh, sorry, sec squared, which is multiplied by dx, which is just du over sec squared x, right? The sec squared x cancels, so we have the integral of u to the 5 times u squared plus 1 du, which is an easy thing to integrate because that just gives us, if you multiply u to the 5 into u to the 2, just u to the 7, which when you integrate is u to the 8 over 8, plus u to the 5 times 1 is just u to the 5, so that would be u to the 6 over 6. And when you substitute back from the original u substitution, you have 10 to the 8x over 8 plus 10 to the 6x over 6 plus c. Right. So in this case, we don't actually need integration by parts, because and I suspect that's the reason why, because we have on the trigonometric functions under the integration sign. So we wouldn't need to, all we would need to do is just find a way to use U substitution to link one of the functions. One, if you have two trigonometric functions like we have here, tan and sec, we just use U substitution to link both to simplify the expression so we can integrate. Unlike all the other example where we had an exponential function, and then we had with the ln there, and then we had the x squared, right? So that's two separate different functions. So that means that this case was particularly easy for us. And yeah. Now, you could try as an exercise using the substitution, the second substitution here that was suggested, right? Try it and see where it leads you. As I said multiple times before, really you don't. These substitutions, it just comes with practice. There's no magic trick. So the more you practice, the more you sort of see which substitution is more advantageous than the other one. Who knows? Maybe if you use the second one, the process is even shorter. So try that as an exercise, and you're free to send me your attempts, and I'll have a look. Right. So, in the interest of time, let's move on to the next question, which is asking us to solve the integral of